Solve the rational inequality algebraically, and in this video we're going to demonstrate the boundary point method. In the first step we want to get 0 on one side and write the rational expression as one fraction on the other side. In this introductory example we already have 0 on one side and our rational expression is written as a single put together fraction on the other. Now in order to find the boundary points we're going to look at the zeros of the numerator and the zeros of the denominator. The 0 of the numerator is the x value that causes the numerator to be 0, and so that would be x is equal to 2. The 0 of the denominator is the x value that causes the denominator to be 0, so that would be x is equal to -1. And these zeros are going to be considered our boundary points. Now we're going to plot these boundary points on a number line and test values in the resulting subintervals. So we pick an x value that is to the left of -1 on the number line. We want to choose a small integer, so -2. We definitely want to keep our calculations as simple as possible. Inside this next interval, we have the x value 0, so that's a good candidate for testing. And outside here, again, we're just picking an integer value that is as small as possible. Anything inside that interval will work as a test subject. Now we test these values back into the original inequality to see if they make a true statement or not. So we'll rewrite our rational expression here. We have x minus 2 over x plus 1, and we want the values that make this less than or equal to 0. And so first we're going to test x is equal to -2, so we plug -2 in for each of these x values. Then we evaluate to see whether or not this is a true statement. In the numerator we have -2 minus 2, which is -4, and in the denominator we have -2 plus 1, which is -1. And we copy-paste the other side of the inequality. Is this true? Well, no, it's not, because -4 divided by -1 is +4, and +4 is not less than 0. So this interval does not work. Now we'll test x is equal to 0 back into the original inequality, so we plug in 0 for both of these x values. 0 minus 2 in the top is -2, 0 plus 1 in the bottom is +1. And now we can see that -2 is what we have on the left, which is indeed less than 0. So since this is a true statement, our test value works, and so does the interval that it represents. And now to test this last interval, we're going to plug x is equal to 3 in for both of these x values. So 3 goes into here, which gives us 3 minus 2 is 1 in the top, 3 plus 1 is 4 in the bottom. And 1/4 is not less than or equal to 0, so this interval does not work. Now we also have to test the boundary points themselves, and again those boundary point values were x is equal to 2 and x is equal to -1. So when we test x is equal to 2, we put 2 into both of those x values, which yields 0 in the top, 3 in the bottom, and 0 divided by 3 is 0. And since 0 is equal to 0, this boundary point is going to be part of the solution. Now we'll test x is equal to -1. -1 goes in for both of these x values, which yields -1 minus 2 in the numerator is -3, -1 plus 1 in the denominator is 0, but anything divided by 0 is undefined. And since this is an undefined quantity, it doesn't make sense to think about whether or not it's less than or equal to 0, so we say this is not a true statement. And the x value that caused that to happen, this boundary point, is not part of the solution set. Now it's time to put all this together and clearly state our solution. Remember, this leftmost interval does not work, so the solution set begins with -1, the boundary point. Because -1 did not work, it's not going to be part of the solution, so we leave it out with a parenthesis. This entire interval does work all the way up to the next boundary point, which is 2. +2 did work in the original inequality, so we do include that in the solution set. This rightmost interval did not work, and that takes us all the way out to +infinity, which means that this is our entire solution. In order to check this answer, let's consider the graph of the rational expression on the left-hand side. Let's set that equal to y so that we can graph it, and the outputs of this rational expression on the left will be represented by the y-coordinates of the rational function that we're graphing. To graph a rational function quickly, we can just look at the vertical asymptote, horizontal asymptote, x-intercepts and y-intercepts. There is no oblique asymptote on this rational expression because the degree of the top and the bottom are the same. The vertical asymptotes occur at the zeros of the denominator, so the vertical asymptote here is going to be at x is equal to -1. When the degree of the top and the bottom are the same, the horizontal asymptote is going to occur at the y value, that is the ratio of the leading coefficients. The leading coefficients here are 1 divided by 1, so 1 divided by 1 is 1. The x-intercepts occur at the zeros of the numerator, so we have x is equal to 2 will cause the y value output to be 0, and the y-intercepts occur at the y value that results when we plug in 0 for x. And when we plug in 0 for x here, we're going to get -2 over 1, which is -2. So now that we have these values, we can plot them on the Cartesian plane. X is equal to -1 is this vertical line. Y is equal to +1 is this horizontal line. 2, 0 is the x-intercept, and 0, -2 is the y-intercept. And when we approach these asymptotes and connect these intercepts, we'll see that the rational function looks like this. The solution to this rational inequality is going to be where these y value outputs are less than or equal to 0. In other words, where's the graph under the x-axis? Well, these y values are less than 0, and that's really it. We also need to consider the x-intercept. This x-intercept here has a y value that is equal to 0. Well, equal to 0 is allowed in this inequality, so this x value is going to be part of the solution. So to clearly state the solution set, the x values that cause the y values to be negative are the ones that start at -1 and go to 2. We do not include x is equal to -1 because at -1 we actually have a vertical asymptote there. -1 is a domain restriction. This function doesn't even exist at x is equal to -1, and so certainly that could not possibly be part of the solution set to the rational inequality. But when we get over here to x is equal to 2, x is equal to 2 causes the y value to be equal to 0, but equals to 0 is allowed, so 2 is part of the solution set. And when we look at the graph of the rational function, we can clearly see that the solution we came up with a moment ago is correct.